I think this is about where we got to last time. We're talking about the simple gas laws, and again, pressure, volume, temperature, and moles, and a bunch of these, and all the simple gas laws, 2 of those are constant. And we're only looking at how 2 variables basically interact. How does pressure interact with volume? How does volume interact with temperature? And then number of moles in volume is the other one that we look at. So I believe I brought up the simulation because we talked about Boyle's law, which reminds me I need to load the simulation. Talked about Boyle's law. Yes. Yeah. And so this is the experiment basically that Robert Boyle did, is he had some amount of gas trapped in this tube. He added mercury to it. And then as he adds more mercury to one side, mercury, by the way, is very dense. We have some. If you want to experience how dense mercury is, I have it in the lab. So as you add more and more mercury on this side, this end's plugged, so this gas can't go anywhere. And this gas gets more and more compressed. And so we can describe the pressure based on the height of the column of mercury that's squishing it. And that resulted in a graph like this. Obviously, Robert Boyle didn't have Excel, but he would have plotted it out by hand, something like this. And so with the smallest amount of mercury, lowest pressure, see, the volume was the largest. As you add more and more pressure, the volume decreases and has diminishing returns as you get to really high pressures. So that's just plotting pressure versus volume directly. I should change the order of these slides. If, though, we take this and instead of plotting volume versus pressure directly, we plot the volume versus 1 divided by the pressure, it magically becomes a straight line. Meaning that there's a inverse relationship between these two. And a direct relationship, because it's a 1-to-1 change. So if I double my pressure, or so if I double my pressure, if I double my pressure, which higher pressures would be, this is 1 over. So higher pressures are over here. This is breaking. Oh, because these are the smaller numbers. Yes, okay, good, thank you. These are the higher pressures because this is the smaller number. So it's 1 divided by a larger number. So as we increase the pressure, it's actually going this way, the volume decreases. So going from like 0.03 down to 0.015, that should cut the volume in half. So that was P1V1 equals P2V2. Right, and we want to tie this all back to the kinetic molecular theory that we looked at before going into these simple gas laws, because this is the best simple description of what's happening with gases. So I've got all these particles inside of my cylinder here, and I can put a weight on top, and the cylinder is going to decrease in volume a little bit because I've added more pressure. If I double that pressure, then the volume gets cut in half, because these little particles in here have to apply more force to hold that weight up. And as you decrease the volume, the amount of collisions increases because there's smaller distance to travel. We're going to use diving examples for a bunch of these. This is super important to know for diving because you may not know this, but water is a lot heavier than air. And because it's so much heavier, that means the pressure that you feel from water is a lot higher than we feel from the air. Like right now, we're all experiencing about 14.7 pounds per square inch. So on every inch of your body, in every direction, there's 14.7 pounds of air pushing on it. And that's because of all of the air between us and space. So all of that air is sitting on top of us, right? Miles and miles of air. You go underwater, even just going down 10 meters deep, not again miles, you get an extra atmosphere of pressure for every 10 meters that you go underwater. Way down here at 20 meters deep, that's 3 atmospheres of pressure because it's all of the air plus the water. So if you hold your breath while you're rising to the surface and you rise to the surface too quickly, when you inhale from your breathing tank at the bottom, you've got 3 atmospheres of pressure inside your lungs. And that's fine because there's also 3 atmospheres of pressure pushing on the outside of your body. If you rise too quickly, though, now you've got 3 atmospheres inside of you, and there's only 1 atmosphere on the outside. Now you've got 2 atmospheres, or about 30 psi, trying to explode from your lungs. Yeah, violent. So you have to exhale when you're rising, especially if you're rising quickly. We can also use this to determine depths. If we've got a snorkeler, he has a syringe that's filled with 16 milliliters of air from the surface, where the pressure is 1 atmosphere, takes that syringe down to an unknown depth, looks at the volume of the syringe when he gets down there, and it's down to 7.5 milliliters. So what's the pressure at that depth? And then again, if pressure increases by 1 atmosphere for every additional 10 meters of depth, how deep is the snorkeler? So this is where we use Boyle's law. P1 V1 equals P2 V2. So we know that the initial pressure is 1 atmosphere. And here's a pro tip. Do we need to convert from milliliters into liters? Not for these gas laws. Because I've got volume on both sides, and as long as I put in milliliters on both sides, I'm going to end up with volume divided by volume, and so that cancels out. 16 milliliters at the surface. We want to know the pressure at the bottom, and this is 7.5 milliliters. So dividing by 7.5. It's going to be 2.133 repeating atmospheres equals P2. Now for a final answer, we would round that to 2.1. Now how deep is the snorkeler? So we're told it increases by 1 atmosphere for every additional 10 meters of depth. So that would be for every 10 meters, 1 atmosphere. Maybe it's better to just use the 2.11. Right, so if I take the 2.11 atmospheres though, we do this right now because we have the solution, it's 11 meters. Right, but 2.1 times 10 is 21 meters. So why are those different? Yeah, we started at 1 atmosphere, so the pressure only increased by 1.1 atmospheres. So instead of using the 2.1, because that's the final total pressure, this 10 meters per 1 atmosphere per 10 meters, is for every additional 10 meters, or on top of, or the change in pressure. 2.1 atmospheres minus the 1 atmosphere that we started with, it was 1.1. And now we use this, atmospheres cancels, and we get 11 meters. Questions? Nope. All right. Simulation time. I'm on the wrong one. No, that was the right one. Ideal. Add some particles. We want constant pressure. Yeah, dependent variable volume. Okay, so the next relationship we want to talk about is volume and temperature. So I have down here a magic little bucket, and I can heat things up, and I can cool things down. When I cool this down, the volume decreases because pressure is being held constant right now. This is the same thing that would happen with a balloon. So interesting thing, like a balloon stays inflated because there's exactly the same amount of pressure inside the balloon as there is outside the balloon. So you've got this tug of war of forces between the particles, air particles colliding with the inside and air particles colliding with the outside. So how does that balance change? Energy of the inside particles, energy of the outside particles when I heat up my square balloon. They collide more often, and they're going faster, so they collide harder. So if I add heat to this, if I can add enough heat, it's maybe a little bit hard to tell, but they're moving faster. They also now, though, because the size changed, they have a longer distance to travel. So the pressure inside stays the same as the pressure outside, because we counteracted, or I guess balanced the extra energy inside the balloon by making it take longer for them to go from one wall to the other wall. And then when I decrease the temperature, the particles slow down. So the only way that the pressure can stay the same is if there's a shorter distance for them to travel from one side to the other.
So the pressure stayed the same because they are moving slower.
Yeah. So the pressure stays the same because the volume changes. So I can heat it up. Let's hold volume constant. And now if I increase the temperature, you see the pressure goes up. So now your pressure is 14.3 because we got the same size box. So the distance to travel from one side to the other hasn't changed. But since they're moving so much faster and colliding with more energy, that's a higher pressure. And you go back to locking this. And if I cool it down, the pressure doesn't change. Oop, I break it. Oh, I broke it. Now it's sad. Here we go. So now I can increase the temperature, decrease the temperature. So how would you say that those are related, right? If I increase the pressure, or the temperature, sorry, if I increase the temperature, how does the volume change? Increases. And if I decrease the temperature, volume decreases. So those are directly proportional. That's what we were talking about with that Alex problem also. So this is called Charles' law. Quantified this relationship between gas volume and temperature. So the volume of a gas is directly proportional to its absolute temperature. And this is, in all of these questions, the one place where the units really matter. Temperature has to be in Kelvin. Because if temperature is not in Kelvin, Celsius is a relative scale, so it could, in theory, go to negative infinity or to positive infinity. Because it's not really based on anything other than the temperature that water freezes and boils at. Kelvin, actually, I believe it's this gas law that we get like the first calculations of absolute zero. Yeah. So we take this idea, again, the volume decreases as we decrease the temperature. The other thing that happens is those gas particles are moving slower and slower. And so if you extrapolate that out from like regular temperatures or pressures, if I decrease the temperature more and more, they move slower and slower. And at some point, they have to stop moving. They can't then go in reverse. There's not really a reverse to motion or kinetic energy like that. So you can take all these gases, and if you extrapolate back, they all converge at the same point of negative 273.15. And that's what the Kelvin scale is based on. A change of 1 Kelvin is the same as a change of 1 degree C. But degree C starts with 0 at the freezing point of water. Kelvin says 0 is absolute 0. And so it's this absolute temperature scale that we can use to compare volume changes in gases according to temperature changes. So you could also do this with a balloon and ice water. So you take the balloon, put it in ice water, and it shrinks. You could do this at home. Take a balloon, blow it up, put it in your freezer. It'll get all small. And then you take it out, and it will start to seem like it's inflating by itself, but it's really just the gas particles on the inside picking up heat energy from the surroundings, starting to move faster, and fighting back against the outside pressure. So just like with the simulation, and that's why I start with that, because it's this molecular view that when we're thinking about gases, we got to think about them as these collections of particles flying around. And by changing the temperature, we change how fast they're moving and how much kinetic energy they have. So increasing temperature, you get collisions that are more frequent, and the force exerted with each collision is greater. So if we didn't increase the volume, then the pressure would have to increase because we've got more collisions and they're hitting harder. So that's more force. But by increasing the volume, pressure can stay constant because it takes more time to travel across. Oh yeah, and we'll talk about density of gases later. This is a balloon in liquid nitrogen. Very cold. And then in a hot air balloon, you're actually expanding the volume of, it's like hot gas rises because it has a larger volume for the mass of gas. It actually takes up more space. And that's why hot air balloons rise. So gas in a cylinder with a movable piston has an initial value of 88.2 milliliters. We heat the gas from 35 degrees C to 155. What is this final volume in milliliters? Using Charles' law, pretty simple problem. We just have to plug in our initial and final values, and we'll have one value, the final volume, that we can't fill in. Initial volume is 88.2 over, and we got to convert this to Celsius or to Kelvin. 35 plus 273.15 V2, then 155 plus 273.15. So 88.2 divided by 308.15 times 428. The new final volume is 122, 122.5, which would be 123. And that's why everybody loves formulas, because you just plug in the numbers. I do want to show you something though. What happens if we try to use Celsius for this problem? Now this one's not going to cause the biggest issue. The biggest issue with using Celsius is, what if I said I've got this movable piston and it's, again, 88.2 milliliters, but it starts at 0 degrees C. Can't divide by 0. 88.2 divided by 0? Undefined. What does it mean to divide something into nothing parts? Doesn't even make sense. Now, that's the only time where your calculator will outright just not calculate this. The rest of the time, if I plug in 35 degrees C, you'll get numbers. And so you might think that you've gotten to the final answer. But just like with our other gas laws right here, if I, what the directly proportional means is, if I double the volume, or if I double the temperature, I'll say, what should that do to my volume? Should double it, right? How many times bigger is 155 than 35? I don't know. It's, yeah, something close to 5 times. 4.43. So this is a change of 4.43x. So we would expect the volume to increase 4 times. But again, this temperature scale is not absolute. So if we look at these numbers over here, how much bigger is 428 than 308? And you do that by taking 428 divided by 308. It's actually only a change in absolute temperature of 1.39x. And the larger those temperature numbers get, the harder it is to double the temperature. So if I'm starting with something at 500 Kelvin, I have to increase it by another 500 Kelvin just to double the volume. So it does get harder and harder to double volume as you increase temperature. Anyways, I just think it's interesting. And this is why you get ridiculous numbers when you try to do things in Celsius, because most of the time we're talking about, this is a very reasonable change in temperature, 35 to 155. It's pretty hot, but it's a reasonable temperature change. But to increase by 4.43 times, if you started at, again, that's saying that if I went from 308 Kelvin to 308 times 4.43, so it's saying an ending temperature of 1,364 Kelvin. A much, much larger change would have to take place. So anyways, all that is wrong. This is why you have to use Kelvin. Any questions about Charles' law?
So it's just always better to Kelvin.
Yeah. Yep. Okay, so comparing Boyle's law and Charles' law, the pressure exerted on a sample of a fixed amount of gas is doubled at constant temperature. And then the temperature on the gas in kelvins is doubled at constant pressure. What is the final volume of the gas? Okay, so the first thing that we do is we take pressure and pressure exerted is increased times 2. And again, this is one of those times where picking a number helps to clarify things. So let's say the volume starts at 1. So doubling my pressure, how would that change the volume? Wait, decreasing volume increases pressure. So increasing pressure should decrease the volume? No, we increase, yeah. Oh, I remember this now. Pressure exerted on a sample. The volume has to decrease for the pressure to increase because they're inversely proportional. So this has to decrease, has to be cut in half. That's really what this means. So we go from 1 to 1/2. Boyle's law is inversely proportional pressure and volume. Charles' law is directly proportional between volume and temperature. So we start with a volume of 1, then it'll go down to 1/2. Okay, and then in the second part, the temperature of the gas in kelvins is doubled at constant pressure. So we're increasing the temperature. Temperature and volume are directly proportional. So how should my volume change? So temperature is increased. It would be the same. Yeah, so then basically we would go back to the same initial pressure or same initial volume. And we could do even more to apply numbers to this. If we use Boyle's law and we say P1V1 equals P2V2, again, just picking 1 as the initial volume or initial pressure, and then 1 as the, say 1 liter as the initial volume. So I doubled the pressure. So now this is 2 atmospheres. So V2 is going to be 1 divided by 2. V2 equals 1/2. And then we plug that into Charles' law. Now my V1 is going to be, V1 is 1/2 over an initial temperature, again, call it 1 Kelvin, because that's easiest. And then the final temperature will be 2 Kelvin. And now my V2 will be that. So multiply both sides by 2. 1/2 times 2 is 1. So the final volume of the gas is the same as the initial volume. And this is a good strategy for when it's really hard to think around a word problem like this. Because it's a lot easier to see the numbers and plug them into an equation, even though you don't necessarily need to. Okay. Any questions about that one? That one I know is a lot. Especially thinking about increasing pressure and increasing volume, or decreasing volume. Okay. All right. Constant pressure. Oh, yeah. This is, just reset this. Okay, back to the box. So the last one we're going to talk about is Avogadro's law. And this has to do with volume and the number of moles. Now again, inside this box, this is the same one that we were using for volume and temperature. So again, increasing the temperature increases the size, decreasing the temperature decreases the size. And again, why does increasing the temperature increase the size of the box? Yeah, I got more of my particles hitting the walls. And so if they hit the walls harder, then that makes it larger. If they hit the walls weaker or slower, then that makes it smaller. So what do you think is going to happen if I add more particles at the same temperature? How will that change the number of collisions? Yeah, so for more particles of gas, that's more collisions, right? Every particle that I add is going to increase, add another collision. So I'm just increasing the number down here of light particles, 52. Right? So as I add more, the size of the box gets larger because we're adding more collisions, basically. It's like getting hit with one dodgeball versus getting hit by 12 dodgeballs. It's just more force. Oh, I decreased it too fast. I knew that was going to happen. So I had to avoid hitting that double arrow does it 50 at a time, and it's too dramatic an increase. So now I can decrease it. Again, I'll just decrease it, take particles out, and the size of the box decreases because there are fewer things colliding with the walls. This gas law, I think, is also the one that's the most intuitive if you just think about how balloons work. You blow into the balloon, you add more air, you add more moles of gas, and that's what causes the balloon to get larger. This one's named after Amadeo Avogadro, which, as a sidebar, Avogadro's number, he did not come up with the so-called Avogadro's number, the mole, 6.022 times 10 to the 23. It was named after him, so in honor of him. Partly for this gas law, I think, because it's one way they figured out the number of moles in Avogadro's number, or number of particles in. So volume is proportional to the number of gas molecules. Add more gas, for pressure and temperature to remain constant T and P, then the volume has to increase. Or if you take gas particles out, then the volume has to decrease, and these are also directly proportional. And this is the first time you may have thought of it before, but confronted with the identity of the gas doesn't matter. They all will act, all gases can act as ideal gases. And so this could be number of moles of nitrogen or oxygen or fluorine or xenon, any gas. The effect is the same. So Avogadro's law, I mean, we could probably do this with, I don't know, volume of balloons hard to measure. But as you add more moles, you increase the volume. Again, the one I think that's the most intuitive. The thing that maybe you might not have thought of is that if you double the number of moles, you double the volume. So 0.2 moles to 0.4 moles should be a doubling in volume. Are there any points on here that are like nice to? Not really. And then like volume and temperature, we can extrapolate this back to say that 0 moles would be 0 volume, which makes sense. If you take all of the gas out, there's no more volume of gas. So which of these would cause the volume of a gas sample to increase? Would decreasing the pressure cause a sample of gas to increase? Yep. Pressure and volume are inversely related, so decreasing the pressure would increase the volume. How about decreasing the temperature? No. That would decrease the volume because again, you're slowing the particles down, fewer collisions means a lower volume. What about decreasing the number of moles of gas? When you let air out of a balloon, does it get larger? Letting the air out means you're letting out the gas. Again, fewer collisions. And it's not none of the above. Okay. A little more time. Oh yeah, we could do a problem with Avogadro's law. Chemical reaction occurring in a cylinder equipped with a movable piston produces 0.621 moles of a gaseous product. If the cylinder contained 0.120 moles of gas before the reaction and had an initial volume of 2.18 liters. What is its volume after the reaction? And nicely, we're told we can assume constant pressure and temperatures. And this is also important. The initial amount of gas completely reacts. So we're just making a product. So we're going to have, oh yeah, we want to find the volume. So V1 over N1, V2 over N2. So what's V1? 2.18. And what's the initial number of moles? It says a chemical reaction occurring in a cylinder. Yeah, equipped with a movable produces. It's tricky. They're written in a different order. This is the final. So our initial is 0.120 moles. V2 is what we're looking for, and the final moles is 0.621. So 2.18 divided by 0.12 times 0.621. 11.2, not moles, liters. I shouldn't circle that one actually. It should be 11.3 liters. Because sig figs. Yeah, because we go from about, this one cuts it in half. Oh wait, no, this one doubles it. No, it's times 5. I was thinking 0.06 for some reason. 5 times the number of moles, so about 5 times the volume. And that's part of why it's important to also remember the relationship between these things. If I go from 0.1, which is smaller than 0.6, I should see the volume increase because I increased the amount of gas that I have. So if you look at your answer and your answer is then smaller when the number of moles increases, you should go back and check your calculator and check your calculations. Oh, is this getting into what? This one's actually nice because, again, the units don't matter unless it's temperature. Temperature has to be in Kelvin. Actually, I think I changed this one on purpose for that reason. A scale model of a blimp rises when it is filled with helium to a volume of 55.0 decimeters cubed, which is a weird unit. When 1.10 moles of helium is added to the blimp, the volume is 26.2 decimeters. How many more grams of helium must be added to make it rise? Assume constant temperature and pressure. Okay, the question is, how many more grams of helium must be added to make it rise? How much volume do I need before this balloon will float? Our scale model of a blimp rises when it's filled to a volume of 55.0. So I got to get to 55.0. And because we're working with volumes, numbers of moles, it's Avogadro's law again. So my V2 is going to be 55.0 decimeters cubed. My initial volume is 26.2. And then we're given helium in moles for that initial volume, N2. So in this case, we can do that like a cross multiply kind of thing. But the other thing you can do is, this can be written either with volume on top or with number of moles on top, and it works the same. So you could just flip those from the beginning, and then we'd be solving for number of moles, which would be on top. This is 55.0 times 1.1, and then divided by 26.2. So N2 equals 2.309. That's moles of helium. And so even though like this is a weird unit and you'd have to like figure out how to convert it if you wanted it to be in liters, it doesn't matter. Units of volume are always going to be on an absolute scale, so we can use whatever units. They cancel out. Now the 2.309 moles, you would do this and say that those three are, underline the ones that are sig figs. I think maybe I didn't change the answer for this because helium has a mass of 4. So you multiply this by 4 point, whatever helium is, 4.01 probably. 4.0026, and so that's grams per 1 mole. Oh, so the final number of moles of helium has to be 2.309. But what's the question asking? How many more? So I need to save this for after I subtract my already 1.1 moles. That's what I was missing. So that's 2.209. And then that times, sorry, not 2, 1. 1.209. There we go. 4.84 grams of helium. Man, we didn't get to the problem that I wanted to talk about for Alex. We can skip ahead to it. Part of the reason that I put this in here is if you're ever doing these gas law problems in Alex and they give you weird units like decimeters cubed, if it's a simple gas law and it's just talking about a change in volume, how does that affect temperature? How does that affect pressure? Just leave it in decimeters cubed. Don't convert it. The only thing you really need to convert is, we'll talk about where you need to convert for the ideal gas law, but temperature has to be in Kelvin. Actually, I think it is. Yeah. The simple gas laws are really great if you're talking about a change, because I can say if I know what this gas started as and it changed, a change temperature or a change pressure, then I can figure out what the new volume, temperature, pressure, number of moles is going to be. Or I could say if a change happened, I know what it could be before. But if we can take all of these things and relate them all together with this constant, R, it's the gas law constant, now if we know the pressure and the volume and the temperature, we can calculate the number of moles of a gas. So if I know any of these pressure, volume, moles, and temperature, if I'm missing just one of them, for any ideal gas, I can calculate the last one. So the thing that I wanted to talk about before we end here is there's this R value, ideal gas law constant. It can be defined in a lot of different units. And there's one Alex problem for the I think it's called, they don't call them ideal gas law problems, they call them equations of state, I think. I'm just going to skip ahead because I wanted to show you this. This is the other R value, 8.314, meters cubed Pascal per Kelvin mole. Similar to atmosphere liter per mole Kelvin or Kelvin mole. Generally, Alex problems will give you volume in meters cubed, and they'll give you pressure in pascals or megapascals. They're expecting you to use this R value, right? Because if it's already in meters cubed, this R value has meters cubed in it. And then you just got to convert megapascals to pascals. You can, but you now have to convert all of those other units. You had to go from meters cubed to liters. You had to go from pascals to atmospheres.
I think we're keeping my answer for the problem in either milliliters or liters.
Yes. So there were some problems I did go through and I did, because on my end I can just see basically every single problem. So I went through a bunch of them. Some of them pop up using these units. And you can make your life a lot easier by just using 8.314 meters cubed pascals per Kelvin mole. And then I was going to just give you this. 1 megapascal is equal to 1 times 10 to the 6 pascals, which is something you can look up. And then there were problems too where it would give you the centimeters, the height of a cylinder and the width of a cylinder, and then you have to calculate the volume of the cylinder. The units that you get from that are going to be centimeters cubed, which you can convert pretty easily to meters cubed, and again use 8.314. Anyways, we'll talk more about the ideal gas law and simple gas laws later. But it is very similar to the simple gas law problems in that it's an equation that you plug numbers into. You just need to be using the correct units for whatever numbers you plug in and for whatever R value you're using.